achieve this equation. Basically, in this chapter, in the traditional, we only deal with this equation. And this equation basically is arrived by assuming that every cross-section will remain as a plane after deformation. That is the assumption. And again, this one, the slides has been uploaded onto Blackboard. Okay, so you can quickly just listen and then. So we assume, based upon the assumption, every cross-section originally is a plane, and after deformation, that will tilt it a little bit, but will remain as a plane. So under this assumption, so after deformed, every plane we assume we're pointing to the same center, and that's called the center of the curvature. Okay, and this is a very, very strong assumption, and this assumption actually is not true for bending for large bending, assuming the bending is small. Okay. But that is our model. So based upon this one, we realize there's a plane we call the neutral surface, which has no stress, and that exists between the top and the bottom. So from there we identify, and this is the neutral axis or neutral surface, and we locate our origin to the neutral surface, and from there we measure the distance y. And y, and for example, y at this point the coordinate is y, and that is the information in this formula. Okay. And then by follow up these models we come up with, we know that the deformation or normal strain is in this fashion. That means the normal strain is proportional to how far you're away from the neutral surface. If you would be on the neutral surface, then you experience no stress. If farther away, then the larger the stress. And the maximum will be on the top or bottom, depends on the distance. And furthermore, by using this model, we can verify they only have the normal bending, normal stress, and there's no shearing. Back to our assumption, we assume that the plane will remain as a plane, and again, the plane will locally perpendicular to the neutral surface. So, for example, to here, this one will locally perpendicular to the neutral surface. Okay, so under these situations, that means that any plane will locally perpendicular to the neutral surface. Under this situation, they will point to the same center of the curvature. This is a very strong assumption, and this assumption in general is valid for material like steel, like aluminum, which usually has kind of stiff, very stiff. We call it rigid, most rigid. For material like bamboo, and you know that bamboo is kind of slender and kind of flexible. When we were young in my country, and teacher using the bamboo stick hit our butt if we didn't behave well. Right? So that kind of hit that point, you can see the bamboo changing its shape in air and then touching your, and that's very scary. Under that situation, for those materials that has the large, will experience a very large deformation. That situation, I can tell you, the cross section originally locally normal to the neutral surface, but during deformation, that 90 degrees won't remain as a 90 degrees. So that means that will get more other than 90 degrees. So into that situations, that violate our model. And then in this way, we have to use the different model. And that one, if any cross-sectional plane is not maintaining the 90 degrees, then that means that will locally induce further shear stress. Okay, and that is beyond to this class, and that is the model of the beam. So here we talk about based upon this class, we talk about is this simple model. We call the Euler beam. Am I pronunciation is right? EULER. Euler beam? Euler beam? How do Euler, right? Euler. So this is called the Euler beam model. Okay, so people will ask you, what is this one? You're saying that before and after deformation, any cross section remain locally 90 degrees to the neutral surface. If not, then that is called the Timoshenko. Timoshenko beam. Timoshenko is a Russian scientist, and I think his years is in the early 20s and late 90s, early 20s, and his textbook is very famous, and he was the first person to study this question. So basically from his model, not only the normal strain, but also locally we have the shear strength, and make things very complicated. And then those one kind of give you a head up, okay? So
you do that for advanced mechanics of materials.
Yes, and actually in that one, if I would have time, then I would talk about this one. And in my PhD, when I took the advanced vibrations, my project is working on this one, involving not only mechanics of material, static, but dynamic equilibrium. So this one, if you remember, probably before you born, I'm too old. In the late 1980s, when the space shuttle just started with the technology, they use a lot of they use space shuttle to shuffle a lot of the things to the space station. That time, they beginning the construction of the space station, and a lot of countries participated. Canada contributed. The one big contribution from Canada is they develop and construct a three-arm robot. 1, 2, 3. Okay, and that's a three-arm robot developed by Canada. And that arm basically is, I think they eventually, one is in the space shuttle. I think the other one probably space station, basically to put the things out from cargo space. This one, they make all the things is basically here you could imagine at each joint they have the motor, DC motor to rotate it. And they have to make it very light. And actually each beam is very long, very slim. When they rotate, they must have their topic and to rotating into the destination in a certain amount of the time, precisely stand there. But this arm, the standard is more than 20 feet long. You could imagine once it's within. If that allowing like this, what happened? They're going to hit space shuttle or space station and it won't know. They must control it in this way to just arrive to here and then stop. No, we call the vibrations. Under this situation, the arm is making slender and by nature it has easily deformed and will easily induce the vibration things. This arm has been modeled perfectly using this model, and they implement this model into their control laws, control theory, and to suppress quickly such vibrations. And that is a very famous examples. And that time for people who study mechanical engineering, if for people like me going to the control group, then we apply to we call the robot arms, and 2 beams or 3 beams. And that time, my time is 2 beams, flexible, and then we develop the control theory to not only to do the positioning control, but quickly want to suppress vibration because we won't allow the whole thing is stabilized. No, we want that one be there at the right time and just one-time shot. Okay, so that is the one example here. So back to here, and so that is the formula. And for the curvature of the Euler's model, then that is the curvature. Basically, this one, curvature is the loading divided by EI. EI is the material and the geometry compliant properties. So that means if you would choose the Young's modulus is more rigid, then that means it's hard to bend. I is a moment of inertia. If the I that have a cross section is give you very hard, very big moment of inertia, it's hard to bend. Okay, and designing for this kind of question, they usually start with two things. One is as long as they can improve the structure by themselves, then they can use less rigors in control. And if not, then the remaining issue will go to control theory to deal with. Okay, the same thing here. This one, E and I, give us the selection of the materials, the material properties, and the geometry of the material. That will hopefully, if we want to have the link to be rigid, we better to make this number bigger. Okay, that is a feeling about this.